Hello everyone, this video covers section 3.1, interpolation in Lagrange polynomials or polynomial. So let's start with a theorem. The theorem says the following. Suppose that you have a function that is continuous on the closed interval a and b. So therefore, for each epsilon bigger than 0, you can find a polynomial p of x with the following property, which means that for every function, pretty much you can always find a polynomial that the distance between them is very small. Or this is a good approximation to f of x. That's another way you can look at it for all the x that are in the closed interval. Now, this approximation is called Weierstrass approximation. And geometrically, this is what it means. So this means the following. If you have a function between a and b that is continuous, okay, so the function has to be continuous between here and here, okay. Let's say that this one is f of x. So what it means is that as long as you are in the continuous interval, you can always find a polynomial that it will be close to the function. So this will be p of x, and the distance should be close. So you could have here, for example, this will be f of x plus epsilon. This will be like f of x minus epsilon. So the best way to look at this is that you can always find a polynomial that will be close to the function. And in essence, that's the whole point, not just of this section, but of the whole chapter. We're gonna find different ways to find polynomials that approximate f of x. That's the main idea of this chapter. Now, you actually have done this before in calculus, specifically in calculus 2. Remember, in calculus 2, you still remember that? You have something called Taylor series, and we also did polynomials there. Okay, so a series and a polynomial are not the same thing. They're related, but they're not the same. So now remember, from calculus 2, one of the most famous functions that everybody should remember is this one. Let's say that f of x is e to the x. And from calculus 2, this was equals to the sum from n equals to 0 to infinity of x to the n over n factorial, which this is a series because it goes to infinity, but if you stop this at some point, then we're gonna call it a polynomial. Let's say that now you go only from 0 to k, and then this will be x to the n over n factorial. So now this will be a Taylor polynomial. Now again, from calculus 2, this is the exact representation of e to the x. The issue is that this goes to infinity, so you pretty much whenever we get to infinity, so you want to approximate this function, you can just use the first 5, 10, or 20 values, whatever you want to approximate this. So pretty much what we're going to do in this section, you have done it in calculus in a very specific way, but it's exactly the same idea. This is what I mean. E to the x, you still remember that from your past lives. E to the x look like this. So you have 1, and then the graph looks like that. Okay. Now, from here, let's say that k is equals to 4. You're gonna go only to the fourth term. So therefore, if that's the case, then it will expand this. Then we're gonna have that the polynomial is going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial, okay? Which is equals to 1 plus x squared over 2 plus x cubed over 6 plus x to the 4 over 24. Now, if the value for k was 0, then we would stop here in the first one. Then this will be the second one, the third one, and so forth. So this is what I mean. P0 will be 1. P1 will be 1 plus x. So this means k will be 0, k is equals to 1. So this will be the 0 polynomial, the first degree polynomial. If k is equals to 2, then the polynomial will be P2. This will be 1 plus x squared over 2. If k is equals to 3, then P3 will be 1 plus x cubed over 6, and so forth, for k equals to 4. And the more terms that you add, you will expect the approximation to be more precise. For example, if we use just the constant p0 equals to 1, you can also call it a 0 polynomial. Clearly the graph will be like this. So this is p0 is equals to 1, and you can see the, okay, yeah, this is close to here, but this is way off from here to here. Now, if we use p1, then for p1, it will be a straight line that looks like this, and you can see that now this is still close to here, but now this one is definitely better than this one, approximating this value, and so forth. The more you add, the better it should be. So P2 will look something like this. So this will be 1 plus x squared over 2. Also, it's important to notice that if you're close to 0, the approximations are good. But as you move farther away from 0, the approximations are getting worse and worse, even if you add more terms to the polynomial. The reason why the approximations are good close to 0 is that, if you remember from calculus 2, this Taylor series is actually called the Maclaurin series, and the Maclaurin series is a series or a Taylor series that is centered in 0. So that's why the approximations are good around 0. If you wanted to find a closer approximation, let's say around x equals to 2, then you will have to find the Taylor series around 2 instead of around 0. But again, this is what we did in calculus 2. And what we're going to do now is very similar to this, except we're going to find new polynomials. The Taylor series are still going to be and Taylor polynomials very important for this class. But now we're going to go to see a new kind of polynomials, which you probably haven't seen before. All right, so let's go to now Theorem 3.2. And this is very fundamental for all the stuff we're going to do later on. So here it is. It says, if you have n plus 1 distinct numbers for x, okay, so remember we still have, we're in the x y-axis, so this will be x0, x1, all the way to xn, and n and f is a function that is defined at those given values. So the function will be defined at these specific values. Okay, so let's say you have a function that looks like this. Okay, then there is a unique polynomial of degree at most n, so this is important, where the two are equal to each other. So this is f of x, say that's the function. So this theorem guarantees that there is a polynomial which obviously is not the same, but it matches at those n plus 1 points. And then this will be p of x, or xk. No, it's just p of x. And they match at n points, here, actually n plus 1 points. And this unique polynomial is given by the following. Again, it's important that you remember that it has to be at the most degree n, and the polynomial is going to be given by the function evaluated at that point. So this will be the y values, which you know they match at that point. Then there is this new part, which is going to be the Lagrange polynomials. Now, this is no mystery. This is whatever values are given. So in essence, this part is given, or you can find it pretty easily. This is the part that is new, that you haven't seen before. Change the color, this. And here the notation is very important. So LNOK most of the time is going to be written just like this, as L of k. Okay, so it's important that you know that these two are the same thing. So notation is important. Now, this looks like a total mess, and it's actually not that complicated, like you will see in the next example. It's just pretty tedious to compute these things. That's why we're going to use MATLAB to program this, but you still need to know how to do this by hand for the small values of n. Now, this is the same thing as this. You want to write it in compact form. This is x minus xi divided by xk minus xi. Now, before we do the example, notice that since this is equals to just Lk of x, this is implying automatically this has to be a function of x. So this is k. Notice how all of them have k at the bottom, and on the top, everything is there except for the k. And this is what is going to make it a function of x. So let's do an example to see how this works, and you'll see it's not as bad as it looks. It's just pretty tedious, but it's not that hard. All right, so here n is equals to 2, This is the function, and since the polynomial has to match these points, well, if x is equals to 2, then y0 will be 1 over 2, which is just 0.5. Then if x1 is equals to 2.75, then y will be 4 over 11. You can check that. And this is equals to 0.36. And then if x2 is equals to 4, so this will be 1 over 4, which is just 0.25. Now, since n is equals to 2, we only had to find L0, L1, and L2. And each of them, you will see, will get bigger. So L0 is going to be equals to L2 of 0. And this will be x minus x1 times x minus x2. And on the bottom, see the value, since the value for k is 0, this will be x0 minus x1 times x0 minus x2. And then just plug in the values. This will be x minus 2.75 times x minus 4 divided by 2 minus 2.75 times 2 minus 4. And then you simplify everything, you end with 2 over 3. You can also use decimals if you want to. Times x minus 2.75 times x minus 4. And that's L0. All right, in a similar way, we're going to find L21, which would be x minus x0 times x minus x2. And then the bottom, now since k is equals to 1, this is going to be x1 minus x0 times x1 minus x2. Which in our case, this will be x minus 2 times x minus 4 divided by 2.75 minus 2 times 2.75 minus 4, since x1 is 2.75. And all of this now simplifies to minus 16 over 15 times x minus 2 times x minus 4. All right, so similarly, if we want to find L2, which remember means L22, then we do exactly the same thing. So this will be now x minus x0, this x minus x1 divided by x2 minus x0 times x2 minus x1. And then if you plug in the numbers, this is x minus x2, x minus 2, is x minus 2.75. And then on the bottom, this now will be 4 minus 2 times 4 minus 2.75. And again, you should check, this is 2 over 5, which is also 0.4, times x minus 2 times x minus 2.75. All right, once you found L0, L1, L2, then you can write the polynomial. Remember, we're trying to find a second degree polynomial that approximates 1 over x, and in sigma notation, this is the sum from k equals to 0 to 2 of f of x k times lk of x. So in our case, this will be 1/2, that's the f of 0 times 2/3 times x minus 2.75 is x minus 4, which was the first one. And then the next value was plus 4/11 times minus 16/15 times x minus 2 is x minus 4. Okay, and then the last part is going to be plus 1/4 times 2/5 times x minus 2 is x minus 2.75. Okay, and then all of this, once you do the algebra, simplifies to 1/22 x squared minus 35/88 x plus 49/44. So this will be the approximation or the polynomial. So this will be P2 of x. Now, once you have found the approximation, let's say that you wanted to use it to see how accurate it is to approximate f of 3. Remember, f of 3, since f of x is equals to 1/x, so this will be 1/3, which is 0.333, and so forth. So therefore, this has to be close to P2 of 3, which in our case this will be 1/22 times 9 minus 35/88 times 3 plus 49/44. And once you calculate, this is around 0.032955, which you can see is very close to the exact solution. Now, if you didn't get the last example, here's your chance to redeem all your sins. Let's do another example. The difference between this and the previous one is that in the previous one you have an actual function where you were getting the data from. Here you just have 3 data points, and you're going to use the data points to find a second Lagrange interpolating polynomial. The process is going to be identical. So remember, this is what we call L20, and if we use the formulas, this is going to be again x minus x1, x minus x2, then on the bottom this will be x0 minus x1 times x0 minus x2, and then we do exactly the same thing we did for the other ones. X minus 1/4, x minus 1. The bottom is 1/3 minus 1/4, and then 1/3 minus 1. And again, you should check on this. This is minus 18 times x minus 1/4 times x minus 1. L1 is going to be the same thing, so it will be L21, and it will be x minus x0 times x minus x2, and then this is x1 minus x0 times x1 minus x2. Like I mentioned this already 2 or 3 times. In case you still haven't noticed that part, notice that the k value goes on the bottom, and then you go through all other values, and on the top the x1 doesn't show at all, so that's an easy way to keep track. So then this will be x minus 1/3 times x minus 1, and then this is 4 minus 1/3, 4 minus 1, and this is equals to 16 x minus 1/3 times x minus 1. You can use your calculator and set it up to change from decimals to fractions or fractions to decimal. Doesn't matter, whatever is your style. And remember, you are allowed to use calculators on the exam. Actually, you need to have one. All right, so finally L22. So now this will be just x minus 1/3 times x minus 1/4 divided by 1 minus 1/3 times 1 minus 1/4. And this simplifies to 2 times x minus 1/3 times x minus 1/4. Hence, the second degree polynomial is going to be the sum from k equals to 0 to 2 of f of xk times lk of x, just like the previous example. So if we plug in the values, we will get minus 36, which is 18 times 2. This will be x minus 1/4 times x minus 1. And then minus 16 times 1 is minus 16. X minus 1/3 times x minus 1. And finally 2 times 7 is 14 times x minus 1/3 times x minus 1/4. Now, if this was a quiz, then there is no need to simplify. You can just leave the values. I mean the polynomial like this, and this is perfectly fine. Clearly, this is a second degree polynomial because x times x is x squared. So you can see you have the x squared there. Now, as I mentioned a few times, the polynomial is just an approximation to the function. Okay, so remember the function f of x. So remember this is approximately equals to p of x. So they are not the same. So that means the f of x has to equals to p of x plus some error, which is truncation error. So now we're going to focus on this part. This is what the next theorem talks about. Theorem 3.3 says the following. Suppose that we have the n plus 1 distant x points, okay, in the interval a and b, and then f is a function that has n plus 1 continuous derivatives. Therefore, for each x that belongs to the interval a to b and a number Kasi x, which this value is usually unknown. So this is usually unknown. And when I say unknown, I mean we don't know what this function is. Between x0, x1 to xn, and hence if you go in the open interval, then the function is going to be equals to the polynomial approximation plus this error. So this is what we're going to, there will be the truncation error. Notice that the derivative is evaluated at this function, which is usually unknown, and that could cause some problems. So you have to make many assumptions a few sometimes, like you will see right now. So all of this is the truncation error. All right, so let's do an example. So let's say that f of x is equals to 1 over x, and we go on the interval from 2 to 4. Right, then f prime is equals to minus x to the negative 2. F double prime is equals to 2x to the negative 3. And f triple prime is equals to negative 6x to the negative 4. Now the reason why I only go into the third derivative is that, remember, in the previous example 1 was equals to 2, so therefore 2 plus 1 it will give you 3, because you need the m plus 1 derivative. So if we use the information from the first example, we're going to find that the error is going to be this f triple prime of some Cauchy function of x divided by 3 factorial, which is just 6. And then this will be times x minus x0 times x minus x1 times x minus x2. And for lack of a better name, I'm going to call this g of x right now. Okay, so let's say this is g of x. Then this is equal to minus of Cauchy of x to the negative 4 from here, divided by 6. The 6 cancels, so you end up just with negative. So this part gives you this, and then times x minus 2 times x minus 2.75 times x minus 4. Okay. Now notice the you have x to the negative 4 is a decreasing function, so therefore it has a maximum, and since you're only going from 2 to 4, the maximum actually is going to happen at the point 2. So if you have a function that is decreasing like this, and you go from a to b, the biggest value is going to be in a. So therefore, from here we have that the maximum of Cauchy of x to the negative 4 is going to be equals to 1 over 2 to the 4, which is actually equals to 1 over 16. Now you want to convince yourself that that's the case. The other extreme, which will be 4, you will have 1 over 4 to the 4, and the other one is 1 over 2 to the 4, and clearly this is less. So therefore the maximum that's happening at this endpoint. So that will take care of this part. We still need to worry about this part to make this the maximum error you can make. Alright, so recall just from the last page that we just call g of x equals to x minus 2 times x minus 2.75 times x minus 4. And if you distribute, you actually get x cubed minus 35 over 4 x squared plus 49 over 2 x minus 22. So you should check that. Then if you want to find the extreme values of this, then we use calculus. So you find the derivative and you will set it equals to 0. So the derivative will be 3x squared minus 35 over 2x plus 49 over 2, which you should check these factors to this. And yeah, the factoring is annoying, but it's just algebra. So clearly g prime will be 0 if x equals to 7 over 3 or x equals to 7 over 2. Now to find the maximum, you plug in the critical points, just like you did in calculus 1. You don't have to worry about the endpoints because both of them will give you 0. So therefore you only have to check g of 7 over 3 and g of 7 over 2. G of 7 over 3 will give you 7 over 3 minus 2. 7 over 3 minus 2.75. And then 7 over 3 minus 4. And this is equals to 25 over 1 of A, which is approximately equals to 0.314. Then g of 7 over 2 is equals to minus 9 over 16. You should check this, which is minus 0.5625. So now this one is bigger in absolute value. Okay. Therefore, the maximum error is going to be the following. It will be the absolute value of the third derivative times g of x, which was x minus x0 times x minus x1 times x minus x2. Alright, so this will be less than or equal to 1 over 16 times the absolute value of minus 9 over 16, which this is equals to 9 over 256, which is around 0.03516. Again, remember the maximum this value will be is this, and the maximum this, which is we call gx, will be this in absolute value. So therefore the maximum error will be this. For this particular function, we can actually check to see how accurate this maximum error is. So remember the exact function we had was f of x equals to 1 over x. And then the polynomial, or the Lagrange polynomial that we found, was p2, the second degree polynomial, was equals to 1 over 22 x squared minus 35 over 88x plus 49 over 44. Okay. And the exact value, so if x was equals to 3, the exact value is 1 over 3, which is 0.3333. Let's go to, let's say, 3 or 4 or 5 decimal places. And then, even though this keeps repeating, and the approximation we found was p2 of 3 was equals to 0.32955. Now if we find the difference between the two, so 0.33333 minus 0.32955 is equal to 0.0037a in absolute value, which is clearly less than or equal but clearly less than this value right here, which is 0.03516. Now, it is important to notice that this theorem tells you what's the maximum error you can make. It's not telling you the exact error. So for this particular problem, this is the error. Nah, this one, but it cannot be more than this. And that's it for section 3.1.